Okay, so welcome to the last session of today. Our speaker is Professor Antonis Papapantoleon, who's currently a full professor in mathematical finance at Delft Institute of Technology. Antonis did his PhD in Freiburg and was an assistant professor at the National Technical University of Athens. And he's going to speak on model-free and data-driven methods in mathematical finance. Please take it away and thank you for coming.
Okay. Yeah, thank you very much for the kind introduction and also for the invitation to be here. I like the place and I'm always happy to be back here. So I would like to talk about some joint work I did with several authors over several years. So, well, here is a list of all the co-authors, but as we go along in the talk, I will tell you what is joint work with whom. Okay, so let's start by observing that somehow this talk is a little bit different in, relative to all the previous talks from the morning, the nice course of Christian and Eduardo and all the other talks. In the sense that, well, there is a major shift of paradigm in mathematical finance in the last, well, let's say, 10 years or so. And yeah, it goes as follows. So the old paradigm in mathematical finance, which is still prevalent, of course, it is not outdated. It tells you that you are given a model, and then your task is to do something given this model. So compute the option prices, compute the risk measure, do a hedging strategies, and so on and so forth. Okay, but then you have a model, you assume that this is the correct model, and then you need to do everything else based on this model. The new paradigm is that, well, you are not given the model, but still you have to say something about the quantities as before. So you don't know the model, but then you need to say something about option prices, something about risk measures, something about hedging strategies, and so on. Okay, and then of course, what do you do if you don't know the model? Well, the easiest solution is you want to compute bounds. Okay, so this is somehow the flavor of this talk. So we assume that we don't know the model and we want to compute bounds for certain quantities, in particular option prices. Okay, so, my comment about all the new model, take it with a bit of salt and pepper, right? The old model will continue to be used for, I think for forever, basically, for the upcoming future of mathematical finance. And the new paradigm is also not so new, but it is becoming more and more important in the last, let's say, 10 years or so. Okay, so yeah, maybe I try to specify a bit what do we mean by model free and model specific. So, well, model specific should be somehow self-explained. You have a model, you specify the model. It could be a parametric model, a diffusion, and job process, whatever you like. And then you have to do something with this model. And then there are several flavors of being model free. So I try to articulate them a little bit here. So you could say that, well, starting from here, so let's say you start from a diffusion, but you don't know exactly the coefficients of the diffusion. So you have uncertainty of the parameters, or it is a diffusion, but you don't know exactly if it is a local volatility or a stochastic volatility. So you're uncertain about the model, or you could make it even more general and say, well, I know only that the probability measure, and I want to do something with respect to everything here. Okay. And then model free for us, it will be like, completely model free. Assuming that you observe only prices and you want to do something with these prices, and then you don't have any model anymore. Now, how are these worlds communicate with each other? Well, if you start from the model-free world and you feed it with enough information, you should arrive to a specific model. Okay, of course, this is idealized reality, but in theory, the limit of the model-free world with all the information available, it will be the model-specific world. On the other hand, you can start from a specific model and say, well, I'm uncertain about something. And then if you are too uncertain, you are going to end up here. Okay, so these are somehow the two relations, at least from my point of view, between model-free and model-specific world. Okay, so let's start with a motivating example about the contents of this talk. So Christian talked about a binomial model, like coin tossing in the morning. I want to talk about rolling dices. So assume we are rolling two dices, and we are interested in the distribution of the sum. Okay, so everybody thinks that this is an easy problem because this is a first course in probability theory, right? The distribution of the two. It's fair dices, right? I'm not playing any games here. But of course, this is easy if you assume that the dices are independent. If you assume they are independent, well, then you can easily take a paper and you compute the probability. But if they are not independent, what are you going to do? If they are not independent, you have to choose in what way they are not independent. And there are many ways in which they are not independent, right? You can think, for example, that you roll the one dice and then the outcome of the second one is equal to the same one. This is what we call like they are comonotonic, the two dices, they always yield the same result. You could say again that you roll the first one and then the second one is the complement of the first one with respect to 7. So they are like anti-monotonic, they always yield an opposite result. And you can construct many cases of uncertainty, even in this simple game, right? You just have two dices that you are rolling. Okay. So in the related literature, this is what people call dependence uncertainty. It is the situation where you know the marginals of a random variable or a random experiment, but you don't know the dependent structure. Okay, the dependent structure is completely unknown. This is dependence uncertainty. Okay, so let's put some more mathematics around the same example. So we consider a random vector x1 up to xt. We know the marginal distributions. Let's denote them f1 up to ft. And the dependent structure, as we know from probability theory, is determined either by the joint distribution or by the copula. Okay, if I know either one or the other, I have completely specified my dependence. Now, Sklar's theorem is going to clarify the relation between the joint distribution and the copula. So, if I give you a copula and the marginals, then you can construct a joint distribution, and vice versa. If you know the joint distribution and the marginals, you get a copula so that this holds. Okay, so for the first part of the talk, we are going to understand the joint distribution in terms of copulas. Okay, and then again, dependence uncertainty means that you know the marginals and you don't know the copula. Okay, so good. Now, one main question in this field is, take some nice function f, and you want to construct this object here. So this you should understand as well, let's say this is your random vector where you know the distribution and then you don't know the copulas. This expectation is an integral of f with respect to the joint law or something like that. So this you can write in the end as an integral with respect to the copula. Okay, this is what we mean with this. This is what we mean with this notation here. So, one main question in this literature is take some nice function f and compute, the upper and the lower bound of this expectation with respect to all copulas. Okay, this is a super classical problem in this field. It goes back to the era of Kolmogorov, actually. And in dimension 2, there are very explicit results. In higher dimensions, it depends. This is a long discussion. Okay? I don't want to go into this discussion now. Okay, but we got interested in the reformulation of the problem by Peter Tankov something like 10 years ago, where he said, I want to consider the setting as above. I want to maximize or minimize the expectation of this object with respect to all copulas. But now I'm not completely agnostic about the copula. I assume that I have some partial information about this object. Okay, I have some partial information about this object. And Tankov provided a complete solution for this problem in dimension 2. Okay, and as I said, there is a lot of literature about this problem in mathematical finance with several people listed here, and also in quantitative risk management or insurance mathematics with people listed there. The insurance mathematics literature is evolving basically along the road of copulas. The mathematical finance, it has a branch which is going in the optimization direction and another branch which is going in, which is somehow related to copulas as well. Okay. Okay, so let us start with copula. So the starting point for our work, which was basically part of the PhD thesis of Thibault Lux in Berlin, was to look in this problem of that Peter Tankov described, and see what happens in dimensions higher than 2. Okay, what happens in dimensions higher than 2? Okay, so one main result of this work is the following. So let us consider the following setting. You assume that what is the partial information that Tankov was interested in? You assume that you have here, let's say this is the domain where your copulus is defined, and you assume that you can find some subset of this domain S, and then for every point let's call it ends in the S, you know the copula of this point. Okay, so this is like in dimension 2, this is the plane where the copulus is defined. And then for every point that you take out of this set S, you know the copula. Okay, so you consider here this set where for every point in this set, you know that the copula is equal to this value Q star. Okay, and there are no too hard requirements on what is S, right? It doesn't have to be connected or whatever. Good. Okay, now using this taking this partial information into account, you can compute upper and lower bounds on all the copulas that lie in this set, and they take the form that you have here. So you have basically, for the lower bound, you have like the classical lower Frechet hefting bound, which is this first part. And then you have a second part, which is coming from the additional information. Okay, and the same thing happens for the upper bound. You have the classical upper Frechet hefting bound, and then you get some additional information. I mean, you get an extra term, which is representing the information you have put in your set. Okay. Good. Good. Okay, so this is the picture of what I drew before. Now, so this is one type of information that you can take into account. Okay, you assume that there is a subset of the domain, and you know everything inside this subset. There are also other types of information that you can take into account. So, for example, you can assume that there are certain measures of association in this language, or let's say option prices, and then you know what is the mapping from the copulas to the option price. So, if you map the copula through this option price, for example, you get a certain fixed point. So you know the prices of certain derivatives and to put in the math finance language. In the higher dimensional setting, it is interesting to see what happens if you have like partial information in the lower dimensional subspaces. So you are interested in a 10-dimensional derivative. You have partial information about you know, some 2-dimensional and 3-dimensional derivatives, and you would like to combine everything and you know project everything to the 10-dimensional space. And finally, you can also incorporate information of the following form. So you have some reference copula that you have estimated, for example, from your data. You take some statistical distance, and then you can compute upper and lower bounds with respect to all copulas Q that lie some delta distance from your reference copula. So this is some sort of, you know, some sort of like a confidence interval around a given copula. Okay. Now I have just described sets of copulas and upper and lower bounds on these sets. Now, how could you proceed with this work? So this is the sets that we have defined. You need a partial order on the set. This is already given for copulas. You get your upper and lower bounds, and then if life was nice, these upper and lower bounds would be copulas again. If they would be copulas again, then you have an integration theory, and you have order results that would tell you that basically that the infimum you are interested in or the supremum you are interested in is just equal to evaluating the copula at the upper or lower bound. Okay. However, life is not so nice in science typically. So what happens is that these results, these bounds are not copulas in all the interesting cases. So only in degenerate cases you get copulas. So you need to define an integration theory for these new objects, so which are called quasi-copulas. You need ordering results for quasi-copulas, and then you get, you actually don't get exactly here, you get that, for example, you know, evaluating the expectation at the lower bound is a lower bound for the infimum, and then also you get an upper bound for the supremum. Okay, but this is the best you can do. Okay, but let's look at the numerical results and see how good or bad we are. So the setting is rather simple. You assume that you have three assets. Well, take Black-Scholes model for the marginals. So the marginals are log-normally distributed. So log-normal distribution is somehow the observation of the known marginals that you assume up to now. You also assume that you observe market prices of bivariate, like you know, basket call options of this type. And then you are interested in computing bounds for a three-dimensional asset. Okay, so you have information about this pairwise two-dimensional assets, and you're interested in what happens in the three-dimensional case. Okay, in order to get a reference model to see how good or bad we are, we just assume a multivariate log normal distribution for everything, and you put some correlation. Well, if you do this, then you are completely specifying dependence. Okay, this is the outcome of the numerical experiment. So what you see here is the black line is what you get from your Copula model. So from completely specifying your dependent structure. And what you get from like the discontinuous lines is option prices using the upper and lower Fresher-Hefting bounds, so no additional information. The continuous lines is what you get if you take the additional information into account. Okay, so in this setting, you're generating the prices. You know the marginals, you're generating prices for these two-dimensional assets. You throw the model away, and then you go and compute using your scheme. And you see, well, it gives certain improvements relative to the classical, to the no information case, which is what you should expect. Okay. Now, you can do also more things with this method. So one thing that we did again with Thibault Lux was to compute bounds for value at risk, which is something very popular in this quantitative risk management literature. And with another student, again from Berlin, we used this mapping for option prices or measures of association, and using this, you can detect arbitrage opportunities in the sense that you can have financial markets where two multi-asset derivatives are traded and they are both arbitrage free. But then if you put everything together, then you get an arbitrage opportunity. Okay, so it's a bit delicate situation, but you have now tools to detect these types of arbitrages. Okay, so far so good, but well, not everything is nice. And what is not nice? So the one thing is not nice is that, well, the good functions with which you can build the theory here are the so-called delta monotonic or delta antitonic functions, which are, you can include a lot of examples from finance in this class, but you don't have basket options in this class. So, you have a very nice theory, thank you very much, but the most popular product is out. So yeah, this is not nice, obviously. Second part is more theoretical in nature. So we know from the work of Tankov that these improved Fresher-Hefting bounds are sharp in the sense that they are copulous in dimension 2 in specific situations. And Bernard and co-authors, they could even prove some stronger results in the sense that they get weaker conditions. And what we showed with Thibault is that if D is greater than 3, they are never copulous. But then there is something in between that says that, the results are not copulous, but they are like point-wise sharp. So you have the qualities of this type. So what happens with this improved Fresher-Hefting bounds? Does this hold or not? And third, which is like modeling in finance question is, up to now, we always assume that the marginals are known, but we also want to be model free. So this is a little bit of a contradiction. I mean, are we model free or not? And if we are model free, can we do something which is more general than specifying the marginals? Okay. So the second part of this talk is joint work with Daniel Bartel, Michael Cooper, Thibault Lux, and Stefan Eckstein. And we want to use the optimal transport formulation and see what can we learn about for mathematical finance applications. Okay. Now let us first revisit the classical optimal transport results. So again, we are interested in a problem of this type. Okay, we are given certain assets and the multi-asset derivative, so we want to compute this expectation. So here, you should come here and you want to write this also as the integral of f with respect to some measure mu. This is the preferred formulation in the transport literature. And okay, the classical ingredients for optimal transport is that okay, classical results in optimal transport is the following. You are interested in maximizing this integral here with respect to all probability measures where you know the marginals, but you don't know anything about the joint law. Okay, this is completely analogous to what we had before. We knew the marginals, we don't know the copula. These are exactly the same thing. Okay, and what transport duality tells you is that this quantity you are interested in is the infimum of the sum of these integrals here, where the fi's are bounded measurable functions integrated with respect to the different non-marginal distributions. And then you get a constraint that says that the sum of these functions should dominate your payoff. Okay, so in pure mathematical finance language, well, you consider basically all super hedging strategies with respect to the different functions. And then from all super hedging strategies, you take the minimal one. Okay, and this is equal to this quantity here. Okay, now, well, if you look back to the ingredients that we put in the previous problem, the ingredients we put in the previous problem is that we know the copula at a certain point. Okay, now if we translate this in this language here, what we do know is for every point here, you know the mass that mu is assigning to this box. Okay, you know the mass of this box here. Okay, so well, we can transfer this knowledge then in the optimal transport world. Okay, so we assume that we have certain boxes that should correspond to these points here. We have these certain boxes. Well, if we know the measure that mu is assigning to these boxes, and you interpret the box as a multi-asset digital option, this means that you know the price of this multi-asset digital option. This is what you're going to put on, on the side of the measures. And on the other side, well, you need some strategy in which you are investing in these multi-asset derivatives. Okay, this picture same as here. So now, well, now you have the following. So you have the following transport duality. So now you are interested in maximizing this quantity with respect to all probability measures where you know the marginals. And then you also know the prices of these multi-asset derivatives, these multi-asset digital options. And you can make this a bit more general. You can say that I have also an upper and lower bound for this. So I have like bid and ask prices. Okay, and again, on the dual side, you are getting the infimum over all these strategies where you invest in the marginals, and you also invest in these traded derivatives. So now you can understand these boxes as traded derivatives. And then the constraint is again that the sum of all these functions is dominating your unknown function. Okay, so now you have some more information, but you can still prove, a duality result. And the proof is constructive. Okay, the proof is constructive. And you can also take it a little bit further if you wish. So you can say that, well, I want to include the short selling constraints on this side. So I only take long positions, I never take short positions. And you get results which are more or less analogous with the thing here that you can assume now on the side of the marginals that you don't know exactly the marginals, but you have some sort of an upper bound on the marginals. Okay, so from that way, you can also introduce uncertainty in the marginals in the sense that you could interpret this as having upper bounds on single asset derivatives and not knowing exactly the single asset derivatives. Okay, good. So at least one of the questions we had is solved because you get uncertainty in the marginals. This was point 3 in my list of problems before. So this we get. What else do we get? You can do numerics. Similar to the numerics that we had before. So here I'm considering exactly the same problem as I had before. So you know the prices. You have 3 assets. You know the prices of pairwise single derivatives. And you are interested in the 3-dimensional derivative. And what you see here is basically reference prices again in black. The discontinuous lines are the classical Fresher-Hefting bounds. The continuous lines are the improved Fresher-Hefting bounds in this case. And what you get from this line here and this blue line here is the solution of this transport problem using a method that was developed by Stefan Eckstein and Michael Cooper. Okay, this was the master thesis of a student from Athens, Michalis. Okay, so here there are okay, one point we should make is that, I mean, the optimal transport is actually solving the sharp problem, and the copulas are giving you like a lower bound. Yeah.
Just to understand the pictures better.
So what is the difference between the two pictures? So the example and the bottom is the strike, right? Or I mean,
The difference between the two pictures is the type of information that you have.
okay. And what is in the x-axis here?
So here you have the strike price on the x-axis, you have the price on the y-axis.
And
It's exactly the same as before.
what is the reason that you have more accurate kind of bounce around? I mean, should I understand like 10 is your at the money regime in this case?
10 is the ultimate. No, 10. I don't remember as well, but okay, you're asking, I guess, about this point here, right? Why everything is touching about this point.
Yeah, both seems to be in those region more accurate bounce, I mean, compared to the other areas of the strike. Just
Okay,
maybe.
here everything is touching because this is a point that you know the price, and this is also the point that you're asking the price. So of course, you know, if you're asking for the price that you know, it is normal that this is going to happen, that everything is going to go at the known price. Okay. And why this is sharper here and here, I think this, I would not pay so much attention to this, you know, you could change the numbers like the correlations and where you put your strikes and you could get something different. The main result is one, you get better results than the classical bounds, the no information bounds. And two, you always see that the Copula solution, which is this continuous line, is better than this blue line, which is, you know, numerically solving the optimal transport problem. And this is really, the numerics are simply not working here. This is the message, okay? Because the optimal transport problem is really the solution of the SARP problem, and the other is a lower bound on the SARP solution. So the inequality should have been the other way around, okay? Good. Okay, so, okay, on the mathematical side, you can also answer this point-wise sharpness questions that we had before. Good, but there is still some problem with this framework. There is still some problem with this framework. And the problem with this framework is that if you ask a practitioner, so maybe Jonas, you can tell us something about this, nobody's trading this type of multi-asset digital options, right? This is a fictitious thing that we invented. It makes our mathematical analysis very nice. But, you know, if you give this talk in front of people who really know this stuff, they will tell you, again, well, thank you very much, but we don't have information of this. And then you can try to say, well, I have this Frieden-Lichtenberger and I can try to invert the prices, and this is also not working. Okay, so again, nice results, but still you're not where you would really like to be. Okay, so, well, from here, there are two ways to go forward. There are two ways to go forward. Well, you could try to come back here and change the type of information that you have, that you take into account in this framework. Okay, say that I don't have this type of particular additional information into account, but I really have like an integral over mu that is equal to something. And well, there is a PhD student in Athens who is working actually on this problem right now. And you could also do something different. So I want to talk about the something difference today. Okay, the something difference is really to embrace that we want to be model free. Okay, we really want to embrace that we are model free, and we really don't want to make any assumption about anything that is traded. Okay, so we want to construct a framework where we take the data, and then we want to draw conclusions from just looking at the data and making structural assumptions about the market. Okay, so this is now this joint work with Ariel Neufeld and Shikung Xiang. They are both in Singapore. And okay, what we take into account in this framework is that there exist traded prices of certain things like stocks, single asset options and multi-asset options. And what we observe is the bid and the ask prices of all these things. Okay, so this is a completely realistic framework, right? If I observe a financial market, I can observe these things. Now, we take some function g, which is a mapping from RD to R, and it basically denotes everything that is traded in the market. So trading just in the asset, trading single asset derivatives, multi-asset derivatives, everything is denoted by G. Okay, And now I want to model or I want to describe with this calligraphic Q a set of probability measures that is going to be implied by whatever the prices of whatever is traded in this market. Okay, so I'm going to put in this set G marginal distributions mu I that are giving correct prices for derivatives with payoff GI. So if I observe prices like a bid and an ask price for a payoff GI, and I'm going to consider all the measures mu I that are giving the correct price, so that this integral lies between these two prices. Okay, so I put for single asset options in this measure, in this set Q, everything that is giving correct prices for single asset options. And I do the same thing for multi-asset options, right? If I observe the price of a multi-asset derivative with this payoff, I include this measure if it is giving the correct prices. Okay, so now I have a set of probability measures that is giving correct bid and ask prices for everything that is traded in the market. Okay, now. For a fixed maturity, yes. For a fixed maturity, yes. No martingale transport here. Yeah? Okay, so now you see this is completely driven by the market. I don't make any assumption about the marginals. I don't make any assumption about the joint distribution. I'm only interested in measures that are giving correct prices to whatever is traded in the market. Okay. Well, and I'm interested again in some sort of super hedging duality. I'm interested in the upper and lower bounds of this integral here. The integral is going to give me the price of some payoff F. And okay, the super hedging duality is working as also as before. So you get that the supremum of this price is equal to this function F. So it is equal to the infimum again of all the trading strategies this is trading in the money market account, and this is trading the bid and the ask prices of whatever is available in the market, subject to the condition that the trading strategy is producing something which is greater than the payoff. Okay, again, the same thing as before, right? The setting is a bit different, but the idea is the same. You take all your trading strategies that are producing a super hedging price for your payoff, and then you minimize this, and then you're here. Okay. But now this is, this is a computationally difficult thing, right? If you would like to make a numerical method for this thing, you would need to, I don't know, discretize probability measures or whatever. This is not very nice. But this is a lot nicer because we are now discrete in space, right? Here we are trying to minimize subject to the C, which is a real variable, and the Y, which is just a vector. Okay, so this minimization problem you can write as a linear semi-infinite problem. So you have a linear objective function that you are trying to minimize, and you have also infinitely many linear constraints. Okay, this is the meaning of linear semi-infinite program. And what we are going to develop are numerical methods which are not exact, but they are epsilon optimal in the sense that for the quantity we are interested in, we are going to compute an upper and the lower bound. And then we know that the upper and the lower bound are going to differ by some epsilon. Okay, so we don't.
It's going to be deterministic or in the upper bounds, when you do the numerics, will it be a stochastic type of method or deterministic?
No, it's a deterministic. So from now on, everything is deterministic. Okay. Yeah, so thank you for asking. Okay, now the way we make this work is we are going to restrict ourselves to continuous piecewise affine functions. This is a general definition of the continuous piecewise affine function. I think everybody has a clear view of what is a continuous piecewise affine function, and then a lot of examples like of traded derivatives fit in this class. Okay, so call options fit, basket options fit, all these derivatives fit. What doesn't fit are well, digital options that we had before, but these are rarely traded. And also like options that take square, these don't fit, but they are also not heavily traded. Okay, so a lot of what is liquidly traded in the market fits in our framework. Okay, this is a description of one of the methods developed in our paper. So in the optimization literature, there is this cutting plane method is well known and it is quite effective. And what we developed is an exterior cutting plane method because at some points you need to make cuts which are like exterior to the domain. Okay, but the ingredients are that you assume that prices lie in some bounded set omega. You assume that all the functions you take into account are piecewise affine. And then what the algorithm is doing is you are discretizing the domain by a subset of a finite number of subsets, which you are then basically gradually increasing. And then you have an inner problem to solve that you are solving by mixed integer linear programming. Okay, this is a little bit of minimization jargon, but then the properties are the following. The properties are the following. Under a no arbitrage assumption, you can prove that this algorithm is going to terminate after finitely many iterations, and then you get an epsilon optimal solution. This is exactly what you would like to have. And okay, this is of more theoretical nature. You can also show that this is producing a measure mu star, which is an epsilon optimizer for this for your problem. Okay. Good. So now let's go to some numerical experiments. So the numerical experiments are of the same nature as before, right? You're going to construct artificial data initially by assuming some method. So in this case, we work in 5 dimensions and also in 60 dimensions. We assume that you have, in the first case, you have, I don't know, 439 traded derivatives. In the second case, you have 400 derivatives. And then you put 2 target payoffs, which are of this type, like colon and min or a colon and max. Okay, now you generate prices, assuming that the marginals are log normal, and then you couple everything with a T copula. And that what you're going to do is you're going to generate the prices of this 439 and 400 derivatives taking this specific model. Then you throw the model information out, you keep the prices, and then you start your minimization problems, and then you see what happens. Now we are going to work in 4 settings. In the simplest setting, you take only vanilla options into account, and then gradually you increase the information that you take into account. So first you take only vanillas, then you take basket options, then you take spread options, and in the end, you also take these colon max options. And these are relevant because they have the same payoff structure as your target payoffs. Okay. Good. So this is now the outcome of the numerical method. If you look at these magnified pictures, what you have here, the black line is the model prices. So these are the prices for the target payoff if you use really the model that generates all other prices. And then from out to in, here you get the blue line is just taking the vanilla, like the single asset options into account. This is single asset plus baskets. This is single asset plus baskets plus rainbows. And here you also take these things that have a similar payoff structure into account. Okay, one thing that is relevant is that, well, as you add more information, the uncertainty you have or your no arbitrage gap is decreasing. Okay, so you see here it is very large, here it is tiny. You're almost touching the price if you had full information. And second outcome that we are going to discuss later is that the structure of the additional information is actually important. Okay, so I think we have this simulation, not in the presentation, but in the paper. If you take just the vanillas and then the last bit of information, which is actually same payoff structure into account, you get very good bounds. Okay, and then you can also leave some information out because of time management. Okay, this is a second example, the same story, but now in 60 dimensions. And I think while more or less papers before that, they could go up to dimension 10. Okay, so you get 6 times better results in a sense. And again, you see the structure of the things is the same. So if you take only vanillas into account, you are far away. If you take all the information into account, you are very close even for a 60-dimensional problem. Okay, finally, up to now, everything was actually artificial data. So, you could still have your concerns that the method looks nice, but maybe it does not work with real data. So this is, okay, by the way, the referees had the same point that, well, tell us what happens with real data. So this is real data. It's an index, as Christian was saying in the morning, Dow Jones Industrial Average. And we are also looking at this DATF, so an ETF which is tracking the Dow Jones Index. Here, the 30 assets are the 30 constituents of the index plus the index. And here what you have is the following. Here what you have is the following result. So payoff 1 and payoff 2 is basically two basket options on the index. I think the one has just, 1/30. The weights is like 1/30. The other one has a different weights, just to make things, spice things up. But they give basically the same results. What you see here is, okay, here obviously there is no reference price because you don't know what is the true prices. But what you see is the following. So this 25% means that you use only vanilla derivatives and like only randomly selected 25% of your data, randomly selected 50% of your data, all the data, and then all the data plus, options on the DATF. And what you see is, again, if you put more information, you are getting closer and closer to the prices you would expect. And here there's no reference price, but you see that the arbitrage, the gap between the upper and lower prices is shrinking. And yeah, and that's it. Okay, the gap is shrinking, and I would be happy to take a bet that even if you use, this basket options and you put it in the 50%, you would still get very good results. Okay, much better than using all the vanilla data and no basket options. Okay, so in a sense, the message is, I think the message is clear. The message is use more information if you have it, but be careful about the type of information that you are using. Okay, so if you have multi-asset options which are a payoff not relevant to your target payoff, and you have also something relevant, use the relevant stuff, leave the other out. You gain in computational time, and in accuracy, you're not really losing anything. Okay, it's almost the end of the talk. So these are the 4 papers that I talked about. The first two is with Thibault Lux about this bounds on copulas. This paper with Daniel, Michel, Thibault, and Stefan about this the optimal transport stuff, and the paper with Ariel and Shikun about this really data-driven method. Okay, so before I close my talk, let us advertise that we are organizing the European Summer School in Financial Mathematics in Delft in September this year. The topic is mathematics of fintech, which I think is very relevant for technical institutions like Delft, but also like KAUST, with close connections with computer science and electrical engineering. If you have students or postdocs that are interested, please motivate them to apply. Okay, that's it from my side. Many thanks for your attention.
Thank you so much for your talk. Do we have questions for the speaker? No, not one. There we go.
So thanks a lot for this talk. So can you say anything now if I have just, I would say, instead of having multiple assets, I would say different maturities for the single stock, and say something about path-dependent options from vanilla options?
Yeah, it's a very good question, right? So okay, I mean, we did several attempts on this. So the Copula method is not going to work. We tried, and then the martingale constraint is not easy to write in this Copula form. So, first we try to think about marginals as time, marginals in time, and then a Copula that is connecting them. But now you have the martingale constraint, and this we didn't find how to write in the Copula language. And numerical results tell you that if you don't take it into account, your results are bad. If you try this method, okay, first of all, there are settings, and then you can prove duality, right? I don't think this is a question now. The problem that happens, it's not a problem, but what makes this method fast is that you are actually optimizing over vectors. If you do this martingale optimal transport in the same method, you will have to optimize over random variables. So you are again in an infinite dimensional space. So I know that Shikun and Ariel are working on this problem for I think for certain, not too many time periods. And I think the results are promising. Okay. But that's the best I can say. I'm a simple guy, it's too difficult for me. But thanks for asking.
Thank you. Do we have any more questions? No? If not, let's thank the speaker. Thank you all so much. So that concludes today's session. So we will have a poster session in the hall of this building, which I suppose is close to the entrance and which starts at 5 o'clock with opening remarks from one of our associate vice presidents for research. Thank you again. Thanks.